Okay, we want to talk about maxima and minima of functions of many variables. Now, one very simple and straightforward example is of a paraboloid. Okay, so this is supposed to be a paraboloid with the vertex at the origin. And it's not drawn particularly well, but we understand what this represents. And it's pretty clear that the minimum value of z, in other words, minimum value of the function f of xy that represents a paraboloid, occurs at the origin. Okay, and that's the tip of the paraboloid, if you wish. Okay, and it doesn't matter where I move that paraboloid. It doesn't matter even if I invert it, except that, of course, the minimum, if I invert the thing, would become a maximum. We want to come up with a test for whether a figure has a maximum or minimum value. So the test, if I sketch this paraboloid in the intersection of this paraboloid with the xy plane, of course I'm going to get a parabola. It looks something like this. That parabola, and I said xy plane, it's the xz plane, right? The coordinate plane. The parabola looks like this. And from first year calculus, we understand that second derivative is greater than 0, meaning that the derivative is increasing, and that's the most essential test to see if the function is concave up or down. The second derivative tells you the concavity. And at this point, the first derivative is 0. So there's your second derivative test for a minimum or maximum. Well, in this case, it's a maximum. If the second derivative is less than 0, it would be a minimum, right? So we could say, okay, if the parabola is like this, first derivative is 0, second derivative is negative. And this would be a maximum. And I don't need to explain all that. This is a picture I hope everybody has from first year calculus. I hope you weren't finding maxima and minima just using symbols. I hope you have pictures with them so that you would understand the test. Because you're going to need to understand the test to understand the test we have here. Okay, so what's the second derivative? Well, confined to the xz plane, we can say that the second derivative, which we'll symbolize by fxx, is greater than 0 in the xz plane. So that's a statement that the second derivative is greater than 0. And of course, fx equals 0. Well, we can do the same thing in the xy plane. We have parabola here. Okay, so that parabola, I'm sorry, it's the xy plane, the yz plane. That parabola kind of looks like this. Okay, so this parabola is in this plane. This parabola is in the xz plane. So this parabola is like here, this parabola is like here. And we can then say again, without going into all the detail, we could say FYY. FYY is 0 and also FY is 0. So we'd be tempted to say that anytime your x derivative and y derivative are both 0, and your second derivatives are both positive, you have a minimum. Turns out that's not really true. We're going to see why in a minute. Okay, but in this example, that certainly would work. And we also note, just for reference, that in this case, fxy is positive. And why fxy? What does fxy mean? Well, if fxy was 0, that means that the thing would be flat along this line in the xy plane and this line here in the xy plane. These are 45-degree lines, for example. Going to be related to that. Well, anyhow, there's the idea of maximum, minimum. We want to get a test for maximum and minimum. The other thing is, we could have a surface that does this in the YZ plane, but in the XZ plane goes down like this. Okay, we've got pictures of surfaces that do this. That makes this a saddle point. And it doesn't have a maximum or a minimum at the origin. Even though the first derivatives are both 0, the second derivative is positive, second derivative with respect to y is positive, and the second derivative with respect to x is negative. Concave up in this plane it's concave down. If you're out in the hills someplace, find a place in the hills where you could stand so that the hill goes up if you're going in this direction, and you're in kind of a dip here, but the hill goes down if you move in this direction. It's very, very possible. Okay, so if you move forward or backward, you're going in this direction along this axis. Let's say you're going upward, but if you go forward or backward in this direction, you go down. And there's some point in between there where you could go and stay level. Think about it, and also look at some of the pictures and read your textbook. Well, I don't want to go into a lot of detail on this because people pretty much aren't watching the videos anyway, so I'll try to keep it reasonably short. But what it comes down to is fxx times fyy has to be greater than 0. Actually, greater than or equal to 0, because one of these could be 0 and you still have a minimum point. You'd have more than one, but that's okay. Okay? Why is this? Because if these things have opposite signs like they do here, you multiply them, you're going to get a negative. Okay? So, first you have to have that, and of course, fx and fy have to be 0, because that means it's level in this direction and level in this direction. Now, again, if you're standing on a place where you're in a dip that goes this way, if you move along this axis, it goes this way when you move in this direction. Your second derivative in this direction is going to be positive, second derivative in this direction is going to be negative, and you're not at an extremum, okay? There are directions you can move where you would increase your z value, directions you can move where you would decrease your z value. So the other part of the test, this is necessary but not sufficient for having an extremum, a maximum or a minimum. In order to ensure the test, you have to have this condition, which talks about what happens if you go in this direction or this direction. And this whole thing has to be greater than 0. Okay. If it's greater than 0, you do have an extremum. If it's equal to 0, maybe you do, maybe you don't. If it's less than 0, no way. That means, for example, fxx, fyy is positive. So that means maybe you go in this direction and everything's curved this way. In this direction, everything's curved this way. But if you go this way, everything falls off front and back, okay? That would be a situation where fxx and fyy both have the same sign, so they're positive, so the product is positive. But the square of fxy is big enough that it takes this whole thing negative. Okay, so we call this the discriminant. And there's your test for maximum or minimum. Don't want to say too much more than that.